Hello, we're back looking again at sampling distributions. In the last last video, we talked about distributions that arose from looking at rolling some dice. Let's look at another variation on this. So suppose we consider the experiment of rolling a sample of size 2 from a fair 6-sided die, but it has unusual number of dots per side. Let's say each side is equally likely to come up, but there's a 1 dot on 3 of the sides, 3 dots on 2 of the sides, and one side has 6 dots. So a total of 6 sides there. First thing I would like you to do is make a PDF table and graph for this. Press pause now. Okay, so this would be 3/6 or 1/2 for the probability that you'll throw a 1, 2/6 or 1/3 that you'll throw a probability of 3, and 1/6 for a probability of 6. Of course, those sum up to 1, and the bar graph looks like this, spaced out correctly on a number line there. So that's the PDF. Now compute the mean and standard deviation of this particular distribution. See if you can work that out. Well, if you remember, to get the mean, you take the x times the PDF values here. So 1 times 1/2 is 0.5, 3 times 1/3 is 1, 6 times 1/6 is 1, and we add those up, and 2.5 is the mean. To find the standard deviation, we take each x value minus the mean and square it. So 1 minus 2.5 is negative 1.5 squared is 2.25. 3 minus 2.5 is 0.5 squared is 0.25. 6 minus 2.5 is 3.5 squared is 12.25. Multiply each of these by their probabilities. 1/2 times 2.25 is 1.125. 1/3 times 0.25 is 0.083 with the 3 repeating. And 1/6 of 12.25 is approximately 2.042. Add those up. That is the variance. Take the square root of that, and you get 1.8028 repeating, or 1.8028 at least at 4 decimal places. That is the standard deviation. Okay, and this is rolling a single die. Now suppose we consider the experiment where we roll 2 of these dice, and we're recording the sample mean, which is x bar, of the 2 die rolls. So let's see if we can work out the theoretical probabilities here. First of all, we need to figure out what all the possible samples are. Okay, and then work out the mean and the probability of that. So see if you can do this. See if you can list out all the possible samples and their probabilities. Try to work on it on your own. Press pause. Well, if you get these are the possibilities. There are 3 choices for the first, 3 for the second, so there should be 9 of these. 1, 2, 3, 4, 5, 6, 7, 8, 9. There we are. And I have these in order, die 1 and die 2. So a 1, 1, we have a 1, 3, and a 3, 1. A 3, 3, a 1, 6, and a 6, 1. A 3, 6, and a 6, 3, and a 6, 6. The means here, 1 plus 1 divided by 2 is 1. Halfway between 1 and 3 is a 2. There, average 2 3s, you get a 3. Average 1 and 6, you get a 3.5, and so forth. And these are the means. Multiply those by the probabilities. Now, if it's 1/2 probability of a 1, and then a 1/2 for probability of 1 for the second die. These 2 dice are identical, and they're independent. So we multiply these 2 probabilities together to get the probability that we roll 2 1s, so 1/4. And we do that all the way up and down here, and these are the probabilities. So we're almost to a PDF. The only problem is some of these mean values are repeated, and we need to add those together. So the probability that the mean is 1 is 1/4, so x bar is 1, the probability is 1/4. For 2, there's 2 of them with 2s here, so we need to add these 2 1/6 together to get 1/3. Same way, only 1 3, so that's 1/9 there. 2 of them are at 3.5, that's 1/6 there, and so forth. And we have the probabilities there. So that's the PDF of the x bars. So notice that the x bars have their own PDF table and their own bar graph, which is different than the PDF table and the bar graph for the individuals here. It turns out the mean is the same as the original mean, which was 2.5, 2.5. But here the variance is 3.3. Our variance now will be half that, or the standard deviation is 1.8028. The standard deviation will be that standard deviation divided by square root of 2, which is about 1.2845. So let's repeat this process for samples of size 3. So here are the orders. Here I didn't bother. They're actually, let's see, 3 times 3 times 3. There's 27 different orders here. So if you add these up, you should get 27. But I listed them like this: 111. There's one of those. 113. But I also wanted to include 131 and 311. So there are 3 of those that are the same. A 133, 116, and so forth. And I worked out all those rows. Figured out the mean of each of these group of 3 rows. Add those up and divide by 3 to get these numbers here. And then worked out the probabilities. So for example, to work out the probability of this one here, it's the probability of a 1, which was 1/2, times another probability of a 1/2 for this one, and the probability of a 3 was 1/3. So 1/2 times 1/2 times 1/3. Okay, but then 3 of those times 3, because there are 3 of those. So 1/2 times 1/2 times 1/3, the 3 and the 1/3 times 3, the 3 and the 1/3 cancel. You get 1/2 times 1/2 is 1/4 at 0.25. And similarly, work out the whole table. It takes a few minutes to do that, but we have this. These are our means and our probabilities, so that is the PDF table. Since there aren't any repeats in the means here, this actually is the entire PDF table, and there's the graph. Similarly, I've worked it out for samples of size 4. You can look over this carefully later. All of these are actually different again, so this is the actual PDF table, and there's the PDF graph. So what we notice is that you may have to look back at the tables there and spend a little bit of time with that to verify my calculations. But we see that each time we get a different distribution. Now we started with a distribution that was pretty heavily skewed this way, skewed to the right. And so it takes a little while for this to start to look like a normal distribution, but there it is for individuals. There's the PDF for samples of size 2. There's the PDF for samples of size 3. And here it is for samples of size 4. And we're still getting, the mean is right in here, about 2.5. It's starting to look a little more like a normal, although it's still quite a ways off. It's going to take a larger sample size before this really starts to look like a normal. But if we were to continue this process, eventually this distribution would start to look more and more like a normal distribution, which is really what's called the central limit theorem, which is more work with that as the topic of our next video.